Now that we have this basic handle on the situation and our operators, it's time now to see if we can solve using all of this operator algebra we've been building up for actually what the pure states of L squared are going to be. And our inspiration for doing this is to follow very closely the approach we had developed with the simple harmonic oscillator. There's a very interesting parallel. When I look at what this operator actually is as an operator equation, right, it's a sum of squares of operators. Now, we've already handled pretty nicely, in fact, the LZ part of this. We know what those pure values are. What we really want to focus on is this piece. And what makes this somewhat complicated is that I have a sum of squares of observables. And that's very similar to the harmonic oscillator situation we had. It's very similar to the SHO situation. You might recall there we were trying to solve for the eigenvalues of this Hamiltonian. And the Hamiltonian itself was in this form of, again, a sum of squares of operators. And the way we solved that, we were very successful by actually factoring this into a product, the sum of squares, into a product of linear operators. And the advantage to that was that when we factored things in this way, and there's also an extra piece that came from the commutator, right? And you might recall this was A hat dagger, and this was the A hat operator. The A hat operator. The advantage of this factorization was that then we got basically what were linear equations in our operators, which were much easier to solve. So the idea then is, can I factor this sum of squares into a product of linear terms? And in fact, we can do this in very much the same way as a difference times a sum. Now, in this case, difference times a sum gave me a difference of the squares, which was very nice. In this case, I have the sum of the squares, but I can deal with that pretty nicely, actually, by using the complex number, I. So I can do L hat x times minus I L hat y, and multiply that by L hat x plus I L hat y. And if we quickly multiply this out, you can see this would work, because I'll get Lx times Lx gives me my Lx squared term. My minus ILy times my plus ILy gives me Ly squared, but minus I times plus I is just plus 1. So I will get these two terms. I also get some cross terms that we will have to look at, but those ultimately will be some kind of commutator that we deal with. So let's go along these lines. Let's try this approach. So we can call this the L minus operator, and this I'm going to call the L plus operator. Now the plus and minus is actually not only a nice mnemonic for the formulas, it turns out there's a much deeper reason why these are called L plus and L minus, and we will learn about that later on. But for now, let's actually carry out our computation. So if we actually do multiply this out all the way, L minus times L plus, writing it out, that's Lx operator minus I Ly operator times Lx operator plus I Ly operator. As we had already discussed, the terms that link the like pieces, Lx times Lx is Lx squared. The Ly pieces give me plus Ly squared. This is great. Those are the two pieces that I really wanted. Now there's some additional pieces. I have Lx times plus I Ly, so I can write that as I times Lx Ly. And then I also have this term, which is minus I Ly Lx. So I get the first term with a minus sign, but the operator's in the opposite order. And of course, that is nothing other than the commutator then between these two components. Terrific. So I can now write down what L squared must be. Before I do that, I want to notice something here. I want you to notice something. Of course, I could have written these two factors in the opposite order, right? I could have put L plus first and L minus second. So I'd like to work out what that would give me as well. And I'm going to do one of these, two equations in one type of things. So the lower choice of sign will be this other order. I could have done it in that order, which would have made this one a plus and this one a minus. And if I had done that, I again get Lx times Lx is Lx squared. Very nice. Now I would get plus ILy times minus ILy. Once again, Ly times Ly is always going to give me Ly squared, as I had, but then the plus I times the minus I once again gives me a plus sign. So this term here worked out as well. Now the next two terms, as you might suspect, are going to flip signs. If you look here in my equation, right, the only difference between the upper equation and the lower equation is that there's an extra minus sign applied to I. So immediately I could conclude this really should be plus minus I. If you want to see that a little more explicitly, let's take a look at the corresponding pieces. So I would have Lx times Ly with a minus I. Well, Lx times Ly is the plus version of this, but now it's multiplied by a minus I. So that would give me those terms. And then this term would come in as plus I Ly Lx. And with this minus sign, the Ly Lx would have a double minus sign. It would come in as the plus. So I can actually look at this in either order, and the two different orders have different uses, as we will see later on. So with this then, I think I should just get down the final form for my operator. So my final L squared operator is Lx squared plus Ly squared, which would be this part, which we just learned I can write in my factored form, L minus plus times L plus minus. All right, getting Lx squared plus Ly squared. I have to put this on the other side of my equation, so that will become minus or plus, when I move it on to the other side, I times this commutator, L hat x, L hat y. I'd really like to know what that commutator is. And then finally, that just gave me Lx squared plus Ly squared, right? That I was solving for this part. But I still also, of course, have to include the Lz squared to get the final total L squared. So that is going to be then plus Lz squared. And I can put a nice box around this one here as well. So we now have all the components that we need in line. We've got our factored L squared. We know a lot about our Lz operators. The one kind of remaining piece is to figure out what is this commutator. And we will work that out in the next lecture.